Optimization is the deliberate mathematical process of determining the absolute best possible value of a specific quantity under strict physical limits. In applied mathematics, finding this optimal value drives real-world outcomes. It dictates how a corporation maximizes its profit, how a manufacturer minimizes production costs, and how facilities eliminate material waste. The core mathematical challenge in any of these scenarios is balancing competing variables. Increasing the volume of a container naturally increases the material needed to build it. Lowering a product's price might drive sales, but it simultaneously cuts into profit per unit. These variables constantly push and pull against one another. Finding maximum efficiency in these systems is not guesswork. It is a rigorous, 7-step algorithmic process powered entirely by differential calculus. We will build this algorithm from first principles using two-dimensional geometry, verify our results using the concavity of the resulting curves, and then scale the exact same model to solve a complex three-dimensional engineering problem. As physical and economic systems grow in complexity, relying on trial and error becomes impossible. Applying algebraic proofs and differential calculus is the only reliable method to mathematically guarantee absolute systemic efficiency. We begin with a foundational constraint problem in 2 dimensions. Our goal is to maximize the internal area of a rectangle that is strictly bound by a fixed 40-meter perimeter. This diagram shows our geometric bounds. The quantity we want to optimize requires a specific formula. Here, area is equal to length multiplied by width. Notice the immediate mathematical roadblock. The objective function currently relies on 2 independent variables, length and width. Because they interact, we cannot perform direct single-variable differentiation. To break this roadblock, we use the specific physical limit of the system, the perimeter constraint equation. 2 times the length plus 2 times the width equals 40. We execute a simple algebraic maneuver, rearranging the perimeter equation to isolate width in terms of length. Width equals 20 minus length. We now substitute this isolated value directly back into the objective function. Area equals length times the quantity of 20 minus length. We have successfully collapsed a 2-variable problem into a single-variable system. Geometric constraints provide the mathematical link between variables, allowing us to reduce the objective function into a form that calculus can solve. This graph maps our objective function, which we expand into its standard quadratic form. Area equals 20L minus L squared. This expansion prepares the equation for differentiation. We deploy the first derivative as a rate of change detector, scanning the geometry of the curve to locate its exact mathematical limit. By applying the power rule, we differentiate the area function. The derivative of area, A prime, equals 20 minus 2L. A stationary point is the exact moment a mathematical curve peaks or bottoms out. At this specific coordinate, the tangent line becomes perfectly horizontal, meaning the rate of change is precisely 0. To hunt for that apex, we execute the first derivative test. We set our derivative equation equal to 0. Solving this simple equation reveals that the optimal length is 10 meters. Substituting 10 back into our constraint equation reveals that the optimal width is also 10 meters. We now have a definitive physical result. Among all possible rectangles constructed with a 40-meter perimeter, a 10 by 10 square yields the maximum possible area of 100 square meters. Basic algebra yields numbers, but it is the first derivative that provides the mathematical guarantee that we have located the absolute limit of the system. However, setting the first derivative to 0 exposes a critical vulnerability. It successfully locates a flat spot on a curve, but on its own, it cannot determine if that spot is a maximum peak, a minimum valley, or a saddle point. Looking closely at the apex in this view introduces the mandatory verification phase, the second derivative test, which analyzes the concavity of the curve. We take our first derivative, 20 minus 2L, and differentiate it a second time. This yields a constant value of -2. A negative second derivative dictates that the curve is concave down. This geometric curvature verifies that our stationary point is a local maximum. Conversely, if the second derivative results in a positive value, the curve is concave up, verifying that the point is a local minimum. Relying exclusively on the first derivative is a recognized failure point in high-level mathematics. Concavity verification is non-negotiable. We can now transition from abstract two-dimensional theory to applied three-dimensional industrial engineering. This models a complex manufacturing objective, minimizing the physical packaging material, the surface area of a closed cylindrical can, while remaining strictly constrained to a fixed internal volume. The multivariable roadblock returns. The formula for surface area relies on two independent variables, the radius of the base and the height of the cylinder. We execute our constraint maneuver. We rearrange the fixed volume equation, isolating height by dividing volume by pi r squared. We plug this isolated value back into the surface area formula. It creates a massive equation, but one entirely expressed as a single variable function of the radius, making it mathematically solvable. Despite a significant leap in geometric and algebraic complexity, the logic remains identical. The underlying algorithm, isolate, substitute, differentiate, and verify, is flawlessly consistent regardless of the system scale. These same principles apply to economic modeling, specifically within corporate profit structures. This graph tracks the fundamental economic objective function, profit equals revenue minus cost. Maximizing raw revenue doesn't automatically maximize profit because production costs escalate differently. Applying the first derivative locates the widest differential between these curves. When executing these models, the structural failures are almost always identical. The process breaks down when the constraint equation is ignored, when differentiation is attempted before reducing the variables, or when the second derivative test is skipped entirely. The mathematics of efficiency strictly require discipline. Whether architecting a steel structure, manufacturing precision industrial parts, or pricing a new product, mathematical optimization provides a rigorous method to locate the absolute specific point where a system reaches peak performance.